All right, it's my great pleasure to introduce Anthony back, who will be speaking to us today on using persistent homology to create moduli spaces for chemical compounds. So computational topology for drug discovery. Thanks.
Okay, thanks for having me here. This is joint work with Michael Lerner, who's a professor of biophysics at Earlham College. Okay, so this is the problem context here. So we create new drugs to solve disease. That means that we need to find compounds to run in drug trials. So before we run compounds in trials, we want to run experiments to test their inhibition properties. And we test all compounds on inhibition properties. So we want to find some small set of compounds to try. And that means we want to sort through some very large database of compounds to come up with a likely collection of compounds in order to run through this process. So we're going to look at this step of finding a set of compounds small enough to try. I would point out that without computational resources, you could try and tackle the very large databases directly. That we're talking about is virtual screening. So why do virtual screening? So high throughput screening, physical screening of large number of potential drugs, and it's very expensive. So virtual screening is a computational approach to this problem. So it's typically done based on a lot of knowledge, biochemical knowledge about the problem. It reduces the cost of high throughput screening. And a typical goal for us, and this is just sort of like, these are really rough numbers, is from a database of compounds, we want to be able to select 90% of the potential drugs out of there, and maybe represents 10% of the total compounds in the database. There are lots of existing methods for doing this, looking at structure information, probably chemical information, fingerprinting, etc. One thing that's going to be different about method is that we're going to understand something about the space of compounds, and not just individual compounds on their own. And back to showing how that comes in a little bit later. So just to regroup here, so our goal is to find a set of relevant bioactive compounds in the database. Okay, do this in a particular example. So we're looking for DHFR inhibitors. So DHFR is something that's necessary for reproduction, and we're going to, by stopping from reproducing, we can target various kinds of disease. So an example here is methotrexate for cancer. So we stop cellular reproduction, you stop cancer from being able to grow, right? Application is to as an antibiotic. So bacterial have a similar cellular process, different but very similar. If a DHFR inhibitor, you can use it as an antibiotic. And there's also protozoa like malaria, the same idea, right? So inhibitors represent a large class of drugs, lots of potential uses, from cancer to malaria treatments to treating pneumonia, etc. So the multi-species aspect of this drug makes it more complicated. So we're not just looking for generically bioactive compounds, but we want to understand per species bioactivity. You don't want to target antibiotic targeting E. coli that's also killing the human host, right? And same for pneumonia or malaria. We want precise species targeting of our drugs. Methotrexate is actually is the first historical example of structure-based design. So it's a drug that was designed to via a DHFR inhibitor. Now, so here on the top is the actual in the human, and on the bottom is the drug. So they're similar, but not actually the same. An example of a similar molecule that doesn't work as a DHFR inhibitor. So structure design is hard. Design typically requires a lot of biological and biochemical experiments and knowledge and years of work in order to get right. And I add here that I'm not really speaking from experience, and in fact, so anytime you hear me talking about like biology or chemistry in this talk, it's like I memorized something that someone told me. I'm not an expert in any way in those areas. In any case, it is known to be hard. So methotrexate, which was designed in the 40s and 50s, is still in use today as an anti-cancer drug. So it has a lot of side effects that you hear about when people are on anti-cancer drugs, hair loss, ulcers, etc. The reason is that we don't have a lot of options, right? If drug design were easy, we would design drugs that didn't have these side effects if we could. We use drugs with bad side effects because this didn't work as hard. And a further example, I would say that, so this is the first example where we designed the drug, but then it was actually imaged how it does the interaction. It was being upside down from how it was sort of designed to bind in the binding pocket. So this we kind of got lucky in a certain sense with this design. We thought we were doing one thing, it ended up working, but in a very different way than how it was thought to work. So this is evidence that this is a hard problem to do. We will use some computational topology to help us solve this problem. What are we going to do? For each compound in some database of compounds, we'll calculate a set of topological invariants called barcodes. Barcodes are going to have a metric on them, so we'll be able to say there's a distance between the barcodes. And to assign a distance between compounds themselves. What we want is to create a metric space out of all of the compounds using some selection of barcodes, and show that biochemical properties of the compounds are localized with that space, so that you have a space of you want to have a set of topological invariants so that the distance on those variants, when that distance is small, those compounds function similarly in the human or similarly in a bacterial system. We have some evidence that with the right choice of compounds, you can make progress on this and you can get this to happen. So again, we're not using the barcodes. I'm not going to do a detailed study of the individual barcodes or collection of barcodes associated with a particular compound, but I want to understand the space of compounds and the space of associated with the compounds. And that allows me to make inferences about if I localize certain chemical properties I'm interested in. The actual data set that we're going to use is based on an online database of drug-like compounds, doing a big coarse-grained sorting on it. So we're going to only take those compounds that have one aromatic group and one hydrophobic piece. And we're going to augment this database with literature search of all known DHFR-based drugs across all different species, so human, E. coli, pneumonia, and picarini, and we're going to combine these into a signal data set with about 4,000 compounds. We're going to make these topological invariants to associate these compounds. So I think most of you probably know this, but I'll just go over the particular viewpoint here. Given a filtration of a space, we have maps on homology, and we can summarize the situation with a barcode with respect to that records when topological features are born and when they die in this filtration. we're going to use a number of different filtrations in order to capture different information about the compound. So classic here, RIPS filtration, we're going to filter by, we're going to add in simplicities when they're within a certain distance when they're received. So here's the example. So we start with points. This is the genome. We'll add in edges of increased pairwise distance. So first I add in these edges here, and these edges, and then find these last edges, and because when all the edges of a simplex are in the diagram, we add in the spaces as well. So we're going to record the topological information as it's born and as it's died in the form of barcode. So here we start off with 8 points, that's H0. We connect up some of those points in the first step, so you see some of those disappear. We have fewer connected components. And that last step, we form these circles. So you see the H1 appearing, and then the next step, those circles get filled in with those pieces. So we have one connected component that lives out to infinity, and we have these kind of the birth and death of these circles that happen. That's immediate parameter range. So I want to look at persistent homology with respect to the RIPS filtration captures certain information about a compound. But by a little bit more creative about how we create our filtrations, we can capture more information or different information about the compound. So an example where I'm going to use a different function, centrality. So I'm just going to show you now the value I'll assign to a vertex. So I'm going to assign to these outsidemost vertices the number 0, and then half, 1, and 2. So as I come into the center of the compound, this function increases. And I just want to, we'll extend that to higher dimensional simplicity, so in this case to the edges, just by your interpolation. So what do we see in this case? We start with the 2 pieces at 0, so there's 2 connected components, and it's going to go in from the outside and add in the edges. So I have 2 connected components. Now this step, we created circles, and then one connected component dies, and the 2 circles live on forever. So you see, this is a very different barcode than the one we got from the RIPS complex. And in fact, different filtrations, right, because they're telling me different things about the structure. So what do I learn? How do I interpret the RIPS filtration? I can see that I've learned something about the size of the voids and the number of, at the beginning of H0, I know something about the number of vertices or atoms in the compound, and something about the size of the voids in the compound. For another example, for the filtration by centrality or eccentricity, I learned that the 2 cycles are far away from the center. So they're born, when I'm still relatively far out, before the compound is completely connected. Right? If I let that H0 from when these circles are born, I see that the cycles happen before the compound itself has completely connected up. So they're far away from the center. Barcodes, and you can also engineer barcodes to answer different questions or extract different kinds of information from the compounds.
Sorry, can I interrupt you for a second? So just to clarify, for the second filter complex, you start with a point in the RIPS complex.
I fixed an underlying complex. So here I'm just taking let's say you could say the bond of the graph, and I'm going to filter that.
I see. Okay.
I'm filtering it using a function in case it's centrality. So the center of mass of the compound.
The points are actually the atom molecule. Is that what we should be thinking of?
That's exactly right. So you should think of the points as atoms, and in this case, the edges would be bonds, so atomic bonds.
And distance between guess there is a distance between edges. What's that? That's the bond length, or?
So our bond lengths, but that's not, I'm just fixing all the bonds, and I'm filtering by this other parameter, which is the distance from the center of mass.
And it's measured where each bond just has length 1, is that right?
No, so here, well, in the way I've drawn it, it's sort of, this is just conceptual. This is an actual centrality measurement, and you're calling me out here on a little fudging. So in actual example, I would use, I use both the graph distance in actual example. So I'm actually processing compounds, use the graph distance to measure distance from the center of mass.
Great. All right.
Yeah. A little bit of fudging there on my part. Thank you. Okay. So right here, right, is that one, barcodes are interpretable, and two, you can engineer to extract specific kinds of information in a systematic way from the chemical compounds. So just one small point here is that there's two different metrics floating around, and that was actually just brought in there's a graph metric and an embedded metric, so just the Euclidean distance for the compound sitting in three-dimensional space. And point out that these give sort of different information, and I think in detail, I think about some of these issues. So I have points on a circle, and I have two distances to consider. So I can think of them as sitting in the plane, or I can think of it as an abstract metric space. Filtration on the abstract metric space, and I do that. So here I'm having them 1 unit apart. So these would be first connections I make, 1 unit apart. Now I connect things that are 2 units apart. Then since I filled in a bunch of triangles, we would fill triangles in complex. But then there are these top and bottom triangles also. They are unit 2 apart, and if you think about what I've created, it's actually the void in the middle in the abstract situation that doesn't exist in a planar embedded situation. So classes appear, homology classes appear. Maybe you didn't think about when you're using not the embedded, but the graph metric. So different information. And talking in great detail about, in fact, this specific problem about endpoints on the circle a couple weeks ago. We should take a look at that presentation just in more details about it. So, back to my hand. So, a chemical compound is a finite metric space. So, the points are in 3 atomic coordinates. Points have atomic coordinates. There's metrics we're going to look at. So there's the Euclidean metric, so just exactly think about the distance between atoms, and then there's graph metric, where edge length is the bond length. Functions on atoms, and we're going to use these functions to filter some underlying complex. We want these functions to have intrinsic meaning, so I want them, I'm not going to just use random filtrations, although maybe that would be interesting, but for this use case here, I want them to either come from geometry, meaning they measure some geometric property, like the centrality, or in chemistry, something like partial charge or atomic weight that I can assign to each atom. Okay, so we have a rich set of filter functions to capture a lot of different biochemical properties of the compounds. So geometric filtrations will be things like the alpha complex, Rips complex, and centrality. Vertical filtrations will use atomic mass and partial charge. And I'll just point out that even the geometric functions are sort of implicitly chemical because something like bond, right? The distance between two atoms in the reverse context is determined by chemistry, right? So even the geometric stuff is already implicitly capturing chemical information. Okay. Well, we're going to have to make a number of parameter choices. So this is something that I think to an area where we want to make on the math side, which is a better understanding, so both theoretically and computationally, of multi-filtration. Okay, you like all these different filtrations. I have sort of one giant multi-filtration, but what I'm going to do is fit various parameters and just little long, single lines through this multi-filtration, and kind of do that with a bunch of different choices to control, in some sense, the multi-filtration. So choose things like multiples of the carbon-carbon bond length, because that seems very natural, sort of a natural unit in this problem. Use dimensional cutoff, so I choose 2 or 3 for calculational resource reasons. And for the virtual filtration, we'll need to go up to a maximal distance parameter. I could just go up to maximal distance appearing in a compound. That for a larger compound turns out to be computationally intensive. So I just go up to something like 6 or 8 times the carbon-carbon bond length, and then call it a day for doing the reverse filtration. Okay, parameters. So we end up with hundreds of barcodes for each compound. And this is, fortunate, but sort of that's where we are. So fingers are sort of this terminology for a compound. So I might call this collection of barcodes for a compound a topical fingerprint for the compound. I'm going to organize this collection into a metric space using Wasserstein or bottleneck distance. So here's a reminder, so the bottleneck distance is given, these are basically matching distances. So they look at the error in various kinds of matching. The bottleneck looks at the sum of for the longest error for each the longest error for each bar in the optimal matching, and the Wasserstein just takes this takes the maximal error in the Wasserstein and sums the maximal error for each bar. And I said wrong. In any case, a picture will explain exactly what we're doing. So I'm going to match these 2 barcodes. Here is what their optimal matching looks like, and I'm just either going to take each bar the maximal error, which is pointed to with errors, and sum them, or just the largest total error, which would be that on the right bar, depending on what metric I'm using. I get a metric space for the compounds. Now I want to look at where are the known drugs, right? I did this literature search. My data has both sort of unknown drugs that I want to know something about, as well as ground truth information from literature of drugs that are in use in one form or another. And in space, I want to see if I've localized the known drugs in some sense. If I have, that says I've captured something of the properties of those compounds. So what we're looking at here is this is used by Ayasdiris software. It's the macro output for a data set. So each little dot here represents a collection of compounds. Edges represent overlaps between those collections. And you see in the upper left-hand corner, we have the known human inhibitors, and then we have some 2 smaller groups. So something I've done here has worked, and that it's grouped all the known inhibitors near each other in the space. If I look at E. coli inhibitors, they're in a different region of the space. So I'm able to separate out from antibiotics. And the structural fingerprints are distinguishing between the bioactivity of these compounds, even though the sort of the difference is very subtle if you were to just look at the compounds. So sort of like the mark of success. I've localized the different kinds of compounds according to their bioactivity away from each other, and with species are separated, but interspecies groups are localized, are tightly bound together. Okay, so that's a visualization of this process. I'm also going to try and do this in an automated way, so I can imagine scaling this up to a much larger database. So I'm going to use the fact that the space of barcodes forms an algebraic variety, and I'm going to use functions from that algebraic variety to embed the space of barcodes into Euclidean space, where then I can just apply normal machine learning methods. So the description of this ring, so X and Y are the birth and death points of a bar and a barcode, and you'll notice here that the function X plus Y is not in here because as you take the limit to a zero-length bar, the function value has to be 0. So just some examples of what this looks like. Choose polynomials from this ring of functions up to a certain degree with its cross validation to and I'm just going to use a support vector machine. So really standard and relatively simple machine learning technique. So the confusion matrix. So I have human by the applicant and pneumonia DHFR inhibitors in the data set. We should read this as diagonal are the compounds of each class that I classify correctly, and off diagonal are confusions or misclassifications of compounds. So that 2 in the first row, second column says that misclassified 2 human DHFR inhibitors as E. coli. Here is comparable to state-of-the-art computational chemistry, fingerprint, and simulation-based methods for this data set. Okay, so that's basically the idea here. So from a set of chemical compounds, we calculate a rich set of barcodes. We have a metric on barcodes. So I'm actually using Wasserstein in most cases to form a metric space. We want to understand the resulting metric space and localization within that space to understand what the collection of barcodes are. And we've captured important biochemical information with our barcodes. This method achieves state-of-the-art accuracy for classification for this data set. And additionally, it adds something which is this global view of the space of compounds was inaccessible with previous methods. It has a number of parameters in it, carbon-carbon bond lengths, etc. We would like to remove those parameters and really understand the simultaneous filtration of the compounds by all of the functions that are relevant. And a way of thinking about that is that, let's say I have partial charge and I also have a centrality. So partial charge is a filtration that says how charge is distributed, but I also want to understand like how far away from the center of the charge is, right? Where is it distributed, not just sort of relative partial charges. So interaction, I think, is really important to getting even more subtle signals, and I think we really want to work getting rid of these parameters or making these slices through this multidimensional persistence picture. So something I skipped over here because it's just kind of an ugly story is I will family of barcodes associated with every compound. I combine these into a single metric space by choosing some weights. That process of choosing weights is sort of a good way of doing that. Basically, I did a bunch of simulations and found out different weights to see how localization changed, and chose weights that gave good localization. I'm not really with that story. I like to have something more systematic, and I think the multi-dimensional persistence would help solve this problem. Always faster, more memory efficient, and then are there other functions that we could use to do a better job with the biochemistry? There's some options that I didn't try. The color filtrations, which are the filtrations there are certain structural groups of atoms that have well-known properties in common, and so you can filter by these kind of well-known property groups, right? Like a course level structural filtration. Where are the carbon rings, right? So you can do kind of carbon ring filtration. Weighted versions of the filters we have, weighted by some notion of importance to the problem. Okay, I think one of the really unknowns here, which so the need to really collaborate with chemists and biologists, is that non-intuitive for them. So when I take these results to a biophysicist who studies DHFR in particular over many years, and I'm like, here's how I've grouped them. It's not immediately obvious looking at the chemical compounds why those should be grouped. Why I'm able to isolate out the certain subpopulations, certain subgroups of interactive drugs. So I think it's really we're both measuring something subtle, but we don't really understand what we're measuring with these techniques, and I think that really points to the room for collaboration with other people. I think these drug-like compounds are relatively small. I think it would be really interesting to rather compute power somewhere and look at something like the space of proteins and forming spaces of proteins and understanding how functional groups and protein structure are reflected in the space of proteins. Okay, so this is joint work with Michael Lerner. It was primarily done while I was at a variety of institutions through a series of postdocs, Michael, and we used Dimitri's Dionysus library to do all of our persistent homology calculations. Thank you.
Okay. Questions? So for each of the chemical compounds you created, like you said, hundreds of barcodes for each of them, and I kind of assumed that you would calculate distances between them pairwise. But then you said something that you actually combined all barcodes using weights. So does that mean you made one big barcode?
Well, it means that, so I'm combining the barcodes, I'm combining the distances. So I just take a convex sum of distance to get a distance. Right? So a distance associated with a barcode of a certain type. I want to combine that with a distance from a barcode of a different type. And it's going to combine those by taking a weighted sum, right? With
it's a weighted L1 norm. Yes. You can look at them linearly with weights.
Distances with weights. Yeah. I don't know what the L1 part is, but I'm just
doing it linearly instead of like.
It's like C1 times D1 plus C2 times D2 is the distance, right?
Okay.
So then there's weights C1 and C2. What I did is I looked for localization with respect to sort of how things would localize, group different, the right compounds together, with bias towards setting weights to 0 if they were small, right? So the automated procedure I went through, trying lots of weights. And what ended up happening is that most of my barcodes ended up with 0 weights in the output that you saw, and there were just a handful left over. So out of the 137, I'm not actually using them because most of those weights get set to 0 as part of this process.
Okay.
Yeah. Anything?
Do other people have questions? We'll make other people think of questions. Let me ask one other one. So
Okay.
So compounds, you filtered it in a lot of ways,
Yeah.
maybe like a dozen or so ways. Right? And then for each compound, you have this filtration, which is you can use instead of dozen filtrations, you can think of a filtration in R12, and making random slices of R or various, like you said, hundreds of slices of R12 to get code. Is that right?
That's right.
How are you doing those slices?
So I chose them with respect to what I would call sort of natural scale of the problem. So if like units of carbon-carbon bond length, for instance, right? Fix the underlying, say, risk complex to connect everything that's 2 carbon bond units away, right? Gives me some complex, and then I use centrality to filter it. Kind of natural scale, I would say the carbon-carbon bond length, and I use multiples of that. So 2, 4, 6, 8.
Okay.
Does that make sense? So there's nothing. So I think I could have been more sophisticated with how I chose these slices. But the whole slicing as just a limitation of our understanding of the multi, or something about the right. Our understanding about the multi-dimensional filtration case. I choose some slices. I just do it, and I'm basically unhappy with my choices, but I just do it because that's the only thing to do.
Okay.
Perspective, when we look at hidden multi-dimensional persistence, one we want, that gets rid of parameter choices, but I would really like there to be a metric on whatever we come up with as, metric on whatever your invariants or partial variants are, in order to make these kind of families of shapes. And if the usefulness is one of the nice things about persistent homology is that I don't just use it to study sort of in detail a particular shape, but I can kind of use it to organize collections of shapes relative to each other. And I don't want to lose that going forward. I think that's really, that kind of geometric viewpoint is valuable.
Thanks. The Wasserstein distance, was that the?
Yeah, so I had both bottleneck and Wasserstein in the space that I was doing this looking for constants over, but the bottleneck distances all got set to 0. I don't have a good reason for and like ones were not set to 0. A reason for that, and I can't say, oh, never use bottleneck, right? As a result, what happened in this case for this problem. I wouldn't want to say definitely only use Wasserstein, because I can't tell you why the bottleneck coefficients are not relevant. Is it problem specific? Is it because of something about the DHFR problem, or is it something about like Wasserstein? It's just more subtle. Just use that, right? I don't know. Yeah. Okay.
Let's all thank Anthony for an excellent talk. Thank you very much.
All right, thanks.